The A4Q AI portfolio brings together 3 certifications, each designed to strengthen your understanding of AI from a different perspective. You can start with A4Q AI Essentials to gain a clear understanding of how AI works and how to apply it ethically and effectively. Explore A4Q AI Foundation to deepen your knowledge of AI methods, risk awareness and quality assurance, bridging the gap between innovation and responsibility. And finally, the new A4Q Certified Professional for AI Compliance, a specialized program focused on the EU Artificial Intelligence Act. Here, you'll explore risk classification, governance, conformity assessment, and post-market monitoring, all the key elements organizations need to stay compliant in the new regulatory era. Explore the A4Q AI portfolio and take your next step toward AI you can trust.
Hello everyone and welcome back to the next session of A4Q Testing Summit. I'm Atefa Amlashi and I'm your host in this session where I have Adha Hrusto with me. Adha is an AI engineer with PhD in computer science. She's passionate about AI and how AI can shape the innovation. Today, she's talking about the integration of AI into automated API testing. It's from space to tests. AI-driven automated API testing. I'm very curious to hear about that. Welcome, Adha, to this session, and stage is yours.
Thank you, Atefa. Hello everyone, and I will just start with a question. So what happens when AI helps us build software faster, but our testing process still moves at the old pace? That mismatch creates a risk. APIs change, requirements evolve, and test suites need to keep up. Manual test creation and maintenance can quickly become a bottleneck, and especially when every new endpoint adds more repetitive work. And in this talk, I'll be talking about using AI to close this gap. So turning API specifications into automated tests faster, while still keeping QA engineers in control of quality, coverage, and intent. But before I dig deeper into this topic, I would like to briefly introduce myself. So my name is Adha Hrusto, and I work as an AI engineer at System Verification. My background is in computer science with a PhD from Lund University, and my work has been mainly around machine learning, generative AI, and software quality, with around 10 years of experience in total. And currently, I work on developing agentic AI systems that support employees in their daily work and help improve their efficiency. But I also use the recent AI capabilities to develop innovative QA services that help teams maintain trust in systems that are being built and updated faster than ever before. And in this presentation, I will focus on one concrete example of that work. But I would also like to briefly introduce the company I work for, because it is an environment where my colleagues and I are encouraged to nurture new ideas and transform them into practical, innovative solutions. At System Verification, we work with software quality assurance across the development lifecycle. The focus is to help organizations reduce risk, improve software quality, and build digital systems that are reliable, safe, and easier to trust. That includes quality strategy, test automation, quality insights, and AI-accelerated QA delivery. And internally, we also have an innovation team where we combine QA and AI expertise. And the solution I will talk about today actually came from that environment. It started as an initiative by my colleague, Jon Persson, who who wanted to reduce the repetitive work he experienced as a test automation engineer. And from there, we worked on developing the idea and technical solution. But the goal was not just to generate tests faster, but to create something that could fit into a real QA workflow, to remain understandable for engineers and support better coverage and maintainability over time. But why have we turned towards AI? So it's that we either learn to work with new technology or we fall behind the pace of development. AI-assisted development makes this very clear. Teams can produce and change code quickly, but the ability to understand the impact of those changes does not automatically speed up in the same way. That leads to the second point, that faster releases also bring more uncertainty. The risk is not the only that something is technically wrong. The bigger risk is that the software behaves differently from what users, stakeholders, or API contract actually require. And for QA engineers, this means that the workload increases. More generated code, more endpoints, more changes, and more release pressure all create a need for faster feedback. But faster feedback is not only useful if it's connected to the right things: requirements, expected behavior, and meaningful risks. And this is why current traditional approaches no longer scale very well. Manually writing and maintaining API tests, endpoint by endpoint, cannot keep up with the speed of change. We need some kind of intelligent automation that removes repetitive work, but still preserves the QA engineer's judgment about whether the system is doing what it's supposed to do. But to see why that matters, let us look at the daily reality of an automation engineer working with API tests. A larger part of this work is actually a boilerplate. The endpoint changes, the payload changes, and the expected status code changes, but the pattern is often repeated. Prepare a request, send it, validate the response, check the schema, and handle the surrounding setup. It is all necessary work, but it is not where engineers add the most value. Then there is a maintenance treadmill. APIs evolve continuously, and a small schema change can break several tests. And each failure still requires judgment. Is it the application wrong, or is it the specification incomplete, or the test is outdated? That investigation is important, but it consumes time that teams often do not have. And coverage gaps are another consequence. Under pressure, we usually cover the obvious happy paths first, while boundary cases, negative scenarios, authorization rules, or multi-step workloads are easier to miss. And this is where the gap between the API specification, business expectations, and the actual test suite starts to grow. The numbers here make the scaling problem visible. With around 30 endpoints, and about a day of manual work per endpoint, the first version of the test suite can already take weeks. After that, every API change adds more and more maintenance effort. So the opportunity here is very clear. Can we remove much of repetitive work, keep tests aligned with specification changes, connect requirements to coverage, and still leave the important decisions to QA engineers? We believed the answer was yes, and we decided to explore that by using the latest AI capabilities. But this is where design choices have become important. Using AI is not enough on its own. What matters is also how AI is integrated into the workflow, how transparent it is, and how much control remains with the QA team. So when we designed the solution, we didn't want a black box that produces tests and expects the team to accept them blindly. In QA, confidence comes from visibility, reviewability, and clear feedback, and not from automation alone. So the first design decision was seamless adoption for QA engineers. So QA engineers should not need to change their entire workflow just to benefit from AI. The output should fit into familiar test frameworks and pipelines. The second decision was reviewability. Generated test cases must be readable and structured so engineers can inspect them, adjust them, and understand why they exist. A test suite that passes and is not automatically useful if it is validating the wrong behavior. Next decision was to avoid relying directly on generated code quality. AI-generated source code can be useful, but it can also be inconsistent. Instead, in our solution, we generate structured test models first, and those models are then converted into NUnit code using deterministic templates. We also wanted maintenance and traceability built in from the start. As APIs change, so the system needs to detect what changed and update only affected parts. And finally, each test should be connected back to the API specification and, where possible, to requirements, so the automation remains connected to the intended behavior. So with those principles in place, the solution becomes much more concrete. So now we come to the solution that we proposed, and we called it SpecOps. And SpecOps is an AI-driven solution that generates executable tests from the OpenAPI specification. On the high level, it has 4 core capabilities. And first one is automated generation. So it reads the API specification and generates both contract tests and system tests. Second, we have self-healing. So when the test fails, the system can analyze the failures and suggest or apply corrections to the structured test models, while still surfacing ambiguous cases to humans. Third, we have incremental updates. So when the OpenAPI specification changes, SpecOps detects what changed and regenerates only the affected tests instead of rebuilding everything from scratch. And finally, a fourth core component is domain awareness. So the prompt can include business rules, glossary terms, excluded endpoints, and test data guidance. That allows the generated tests to reflect the domain more accurately than a generic test generator would. Now let us walk through the entire pipeline step by step. And this slide shows the full flow at a very high level. So we actually start, if we zoom in a bit, we start with the OpenAPI specification. This OpenAPI specification gives us endpoints, methods, parameters, schemas, request bodies, response codes, and authentication information. But this API specification is not always perfect, and SpecOps doesn't assume that the specification is actually flawless. It analyzes it and reports some quality issues back to the development team, because those issues directly affect also the quality of generated tests. But once the specification is loaded, the next step is to parse it in the form so that the rest of the pipeline can use it. So in this first step, parsing and extraction, we actually convert OpenAPI document into endpoint models, and these models capture the contract of each endpoint. So all the information, including the path, method, parameters, requests, and response schemas, as well as expected status code. But this is also where we extract dependencies between the endpoints. For example, if one endpoint returns a customer ID and another endpoint requires a customer ID, that relationship is useful for creating system tests later. After parsing, we don't want to regenerate everything every time. Maybe on the first run, we want to generate all test cases. But when there is a change, only a change in the OpenAPI specification, then there is a delta detection, which compares the current API model with the previous run. And SpecOps fingerprints endpoints and schemas, so it can classify changes as added, modified, removed, or unchanged. And this matters because API test maintenance is often where teams lose a lot of time. And if only 3 endpoints changed, the tool should process only those 3 endpoints and not all endpoints. And incremental behavior also makes the output easier to review. The team can focus on exactly what changed instead of reviewing a completely regenerated suite. And now we are moving into AI-assisted test generation. Here, the model is using endpoint information together with business requirements, test instructions, and test data. And the goal is to generate test cases that are useful and not just syntactically valid. That means heavy paths, error cases, boundary conditions, also authorization scenarios, and workload candidates where endpoints can be chained into the system tests. There is also this self-correction pass. So the model output is checked against the expected JSON structure and against the API model, so the pipeline can catch inconsistencies before moving forward. In addition, the generated tests are validated against the provided requirements and the original system prompt instructions. This actually helps us to check whether the tests not only have the right format, but also that they follow what was requested. For example, the intended coverage or domain rules, some naming conventions specific for the project, or some specific testing constraints. Okay, so now in this moment we have test models, and the next step is turning these test models into the executable code. And the test models become the central artifact in the pipeline. And from there, deterministic code generation creates n-unit tests using templates. And this is an important design choice because it reduces risk. So the AI is responsible for the test intent and the structured test model, but the actual test code is produced through a control template. That means we do not rely on the AI to generate arbitrary test code that we then have to trust blindly. And then those tests are executed like any other automated test suite. And the results is just a normal test run with pass and fail information. But the difference is that these results can now be connected back to the generated test models and to the API specification. And the execution results are useful on their own, but they actually become much more valuable when we analyze these failures. And we have the next 2 boxes with where we use AI also first to analyze AI failures, but also to generate the dashboard. So when something fails, SpecOps analyzes the likely cause. The thing is that issue may be in the generated test model, meaning the model should be corrected, or it may be in the API behavior, meaning the API does not appear to align with the specification. And based on this classification, the test model can be corrected, removed if it's not longer valid, or flagged for a QA engineer to review when the case is ambiguous. And these corrected test models are then go back to into the same control generation process. So updated tests are produced from the refined model rather than manually rewritten. And when all the tests are corrected and we only have the flagged one that the engineers are supposed to review, then we generate a dashboard which brings the whole process together. It shows the current state of the suite, like coverage, pass rate, requirements coverage, refinement outcomes. So what was changed and what improved and what still needs attention. So what is important to say here is that this is not just one-time generation process. It is like a life cycle around API test creation and maintenance. So the generated test suite can evolve as the API evolves, while QA engineers still remain in control of the review and decision-making process. So SpecOps, as I already mentioned, has two categories of tests. The first category is contract tests. They validate a single endpoint, so they cover happy paths, error cases, boundary conditions, authentication scenarios, schema validations, and similar. For example, a post to register a customer should return the expected status code, match the response schema, and contain the expected response structure. And the second category is system tests. They are multi-step workflows. They represent realistic business flows where data moves from one request to the next one. For example, register a customer, log in, use the token to purchase something, then receive a ticket ID, and then retrieve that ticket. So generating tests is useful, but for QA teams, the next question is always, can we understand and control what AI did? And as we can see here, so this kind of generating test cases gives us a lot of transparency, but also leaves a lot of control to the QA engineer. So AI in testing must be, first of all, transparent. The goal is not just to generate tests that pass. So useful tests must also be capable of failing when something is wrong. And that is actually what makes them trustworthy. And SpecOps documents decisions in several ways. So through the quality report, validation report, refinement, and report and dependency map. All of these can be inspected by engineers if needed. But the pipeline itself is also visible. Endpoint models are stored as readable JSON. The manifest tracks fingerprints for change detection, and the dashboard aggregates the metrics. And most importantly, the team stays in control. So QA engineers can review and edit the test models before code generation. And they can provide test instructions with domain knowledge, while if there are any ambiguous items, they can be flagged rather than just silently accepted. And then those flagged test cases will be examined by engineers. And also the custom templates are owned by the team, so the generated code follows the project standards. So this is actually the difference between using AI as a black box and using AI as an accelerator inside a governed engineering process. So AI removes repetitive mechanical work, while QA engineers keep the judgment. Which risks matter, which failures are real, and whether the output reflects how the system should behave. With that in mind, let us look at some concrete inputs and how the structured models become deterministic code. So this is, again, just an overview of all pipeline inputs, where everything starts with the OpenAPI specification. But also we can see here how our one part of a test model in a JSON format. So the AI generates actually these structured JSON models that says what the test should do. So we have the test case name, ID, endpoint, method, expected status code, and steps. And then a script and template converts that model into an unit code. So the template is predictable and owned by the engineering team, as I already said. So this means that the final code style, naming conventions, setup patterns, and the validation helpers can be standardized. So this means that AI contributes to the test design, but the code generation is controlled. This gives us both flexibility and reliability. Now I will take you through what this actually looks like in practice with a short demo section. So this demo is based on ticketing system API. It's an API that we internally developed. The purpose is not to focus on this particular domain, but just to show this end-to-end workflow. And what I want you to watch for is how much of the work becomes actually repeatable and visible. So let us start with the CLI, with the full pipeline and the first analysis run. So here we start with the SpecOps CLI. The first command analyzes the ticketing system API. It parses the OpenAPI file, extracts the endpoints, and creates a quality report. And in this example, 18 endpoints are extracted. So this is the first run, and all endpoints are new because there is no previous manifest to compare against. Then we generate models. For contract tests, the tool runs generation per endpoint and produces 47 contract test cases. And for system tests, we have a bit more complex workflow, which starts by extracting dependencies and generating first base test cases and enriching each of them into the actual system test cases. And the important point is that this is a repeatable command line workflow. It can be used locally by a QA engineer or integrated into continuous integration pipeline, so that generated artifacts and reports are produced automatically. In the next example, we have running the incremental command, so where there is a change in the OpenAPI specification. And here SpecOps compares the current endpoint fingerprints with the previous manifest. The result is very specific. So 2 endpoints were added, and one of them was modified. And this allows the generation step to skip the unchanged endpoints. So instead of processing all 18 endpoints again, it generates tests for the these two new refund endpoints and merges the schema change into the modified product endpoint. And this is exactly the kind of maintenance support team needs. The tool doesn't flood the repository with unnecessary changes. It updates the affected files and leaves the rest unchanged, which makes code review much easier. And we can see in the overview here that we have updated or added. So first added test models for two new endpoints, and one of the test models have been modified according to this change in the endpoint, so schema change. I would also like to show the generated dashboard because it gives a very good overview of the entire process. And here we can see different metrics, and these top metrics are designed to answer the first questions stakeholders usually ask. So how many endpoints did we find? What is the contract coverage? How many test cases were generated? What is the requirements coverage? And what is the latest pass rate? And this view is very useful because it turns a generated test suite into something measurable. It gives the team a quick way to understand coverage, progress, and remaining risk. And then next, this part of the dashboard, we can examine test coverage in a more detail. So we can get an overview of the coverage for contract tests, for system tests, a number of total test cases and test steps for each of the categories. But also there could be some uncovered endpoints, and that, for example, and for these endpoints, the SpecOps didn't generate any of the tests. And in a way, this may be intentional. For example, if it's about utility or test-only endpoints, which could indicate gaps that need attention. In the next part of the dashboard, we can see how the refinement process went. As we can see here, after the refinement and after correction of the test models that were being flagged for the update, we have like around 19% of the improvement. And now 44 tests were updated, but still we have like 29 tests that are flagged, and they need to be examined by QA engineers. What is also important here to mention that failed test is not actually a bad test. It is not automatically an API bug. It is a signal that needs classification. And some failures happen because the test model expected the wrong value or used incomplete data. Those can be corrected, but some failures reveal possible gaps or inconsistencies in the API behavior or specification. And those are flagged, like here, like as it is shown in the dashboard. And these flagged are left for human investigation. In the original dashboard, it is possible to expand each of these categories and see details of each run, of each test run. And the final section of the dashboard is requirements validation. So this view cross-references business requirements with the API endpoints defined in the OpenAPI specification. In the example, 6 requirements are fully covered and 1 is partially covered for the partial requirement. For the partial requirement, the dashboard explains what is missing. For example, there may be no explicit endpoint for viewing wallet balance or transaction history, even though wallet and transaction handling is a requirement. And this is valuable because it moves the discussion beyond test counts. A suite can have many tests and still miss an important requirement. And requirement validation helps teams to see whether the API itself supports the intended behavior and whether the tests reflect that behavior. And for product owners, architects, and QA engineers, this creates a shared view of coverage and gaps. And now I would like to just briefly summarize all what I've talked about in this presentation, some of the main ideas. So what we can achieve with a solution like this is that AI can help us to eliminate a significant amount of boilerplate in API test creation. That frees QA engineers to focus on review, risk, edge cases, and domain knowledge. And what is important also is transparency. It is essential. Reports, diffs, dashboards, endpoint models, and requirements mappings makes this process inspectable. And what is, I would say, one of the most important points is that the QA engineers stay in control. The goal is not to replace expertise. The goal is to scale expertise across more endpoints, more changes, and faster release cycles. So one overall message is that AI-driven API testing can help us match the pace of modern development, but only if it's designed with structure, traceability, and human control from the beginning. So thank you for listening. And if you want to discuss this approach in a more detail, compare it with your current API testing workflow, or explore where AI could support your QA process. And please reach out to me or my colleagues at System Verification. And you can find our contact information on this slide. And now I open floor for the questions.
A very relevant topics for teams looking to improve both speed and quality in modern software delivery. Thank you, Adha. I can see that we have some questions. How do you make sure that AI does not just generate tests that pass, but tests that are actually useful?
Yes, thank you for that question. That is a very important, because a test that always passes is not necessarily a good test. In fact, one of the challenges with AI-generated tests is that AI can sometimes optimize toward producing something that looks correct and passes, rather than something that truly validates the system. And we need to be aware of that. And for us, the goal is not just to generate passing tests. The goal is to generate tests that can reveal when the API does not behave according to the specification, requirements, or some expected business flow. And this is why we keep the process based on structured test models, traceability to the OpenAPI specification, and validation against the requirements. And as I mentioned multiple times, we also keep QA engineers in the loop so that they can inspect the generated test cases, and if needed, adjust some domain-specific assumptions and decide whether a failure is a real defect, maybe a test data problem, or something unclear that needs investigation.
Thank you. And what are the main challenges when generating tests from OpenAI specifications?
So one of the main challenges is that OpenAPI specifications are not always complete or precise enough. They may describe the endpoints and schemas, but they often do not fully capture business rules, realistic data, constraints, or how endpoints are connected in real user workflows. Another challenge is also understanding the intent. It is quite straightforward to generate a request from a schema, but it is much harder to know what behavior should be tested, what edge case matter, and how one endpoint depends on another. And that is especially important for system tests where values need to be captured from one response and reused in later steps. And that is why we do not treat the specification as the only source of truth. We also allow business requirements, test instructions, and domain knowledge to guide the generation. And when AI is uncertain, the system should make that visible through the reports and these dashboards that I previously showed, and flag items, rather than pretending that everything is correct. So we will still need QA engineers who will say the final or make the final judgment.
Thank you. And thank you everyone for joining this session. If you like the presentation, please do not forget to vote for this presentation. You can scan the QR code that you can see on the screen and vote for the presentation. Vote for Adha. It's already the second day of the A4Q Testing Summit, and we still have many interesting presentations waiting for you. You can find the full program on our website, and if you missed any presentations, you can rewatch them on our YouTube channel. Thank you very much for joining.
The A4Q AI portfolio brings together 3 certifications, each designed to strengthen your understanding of AI from a different perspective. You can start with A4Q AI Essentials to gain a clear understanding of how AI works and how to apply it ethically and effectively. Explore A4Q AI Foundation to deepen your knowledge of AI methods, risk awareness and quality assurance, bridging the gap between innovation and responsibility. And finally, the new A4Q Certified Professional for AI Compliance, a specialized program focused on the EU Artificial Intelligence Act. Here, you'll explore risk classification, governance, conformity assessment, and post-market monitoring, all the key elements organizations need to stay compliant in the new regulatory era. Explore the A4Q AI portfolio and take your next step toward AI you can